Hi guys, and welcome to this virtual lecture course on Quantum Condensed Matter Physics. I'm Dr. Andrew Mitchell, and in this lecture we'll be talking about the second quantization formalism used to describe quantum systems involving many fermionic particles. We introduced the basics of this idea in the last lecture. We considered a single quantum orbital which can either be occupied by an electron or not occupied. We have 0 or 1 states that describe our qubit manifold. We saw there how we have a two-dimensional Hilbert space spanned by these two states, 0 or 1, and we saw how we can define ladder operators, which in this case are referred to as creation or annihilation operators. These operators create an electron in the orbital or destroy an electron in the orbital. We're confined to the two-dimensional Hilbert space because we can't destroy an electron if it's not there in the orbital, and we can't create an electron if there's already one in that orbital, thereby embodying the Pauli principle. In this lecture, we'll expand and generalize this first to two particles and then to many particles. This will rely on developing the operator algebra, which are encoded in the fermionic anti-commutation relations. We'll also see how we can construct from these annihilation and creation operators for the fermions number operators which count the number of electrons in a particular quantum orbital. We'll construct an underlying basis which will be spanned by these occupation numbers, so that when we generalize this to a many-particle system, we can simply describe a state by how many electrons are in each one of the orbitals. We'll see that this is a mutually commuting eigenbasis for the states, and that when we write down a given Hamiltonian, we can use these basis states to construct the eigenstates of that Hamiltonian. This is a very generalized and powerful framework. It is elegant, it is efficient, and it's compact notation. In this lecture, we need to go to the beginning and really build up this basis from scratch. We'll be going through some quite technical stuff in this lecture to try to develop the basics, but we only have to do this once. In this lecture, we'll develop the formalism, and then in the future lectures, we'll just be able to apply it. The point of going through this in detail in this lecture is then we don't have to do this every time. We just do it once, and then we can simply use it. And, as we'll see, using the formalism is actually very straightforward and simple, and that's the goal. So let's get down to work.
Okay, so in this lecture I want to talk about second quantization for systems of many fermions. However, let's just recap what we studied in the last lecture. So this looks like a very complicated and busy slide, but it's basically a one-slide recap of everything that we studied in the last lecture, which sets out the formalism, if you like, for a single particle. And we're going to, of course, build upon this rather heavily in what comes. So let's just recap this. So first of all, we're talking about a Hilbert space which is two-dimensional, meaning that we have basically qubit states, either 0 or 1. Now we can think about this as being a fermionic state that is either occupied with an electron or not occupied. We're not considering spin yet, we're just considering is the particle there or not. So the Hilbert space is spanned by these qubit states. In Dirac bracket notation, we have a state 0 or we have a state 1. And according to Dirac bracket notation, we have the concept of Hermitian conjugation, which is defined by this dagger operator, which turns the ket into a bra. We can do this for either the 0 or the 1 state. We assume as a fundamental tenet that these states are orthonormal, meaning that if I take the inner product with itself, I get 1, but if I take the inner product of a state with any other states in the basis, I get 0. We also take these states to be complete, meaning that they span the entire state space. I can define, therefore, an identity operator, which is a projector onto all possible states of the system in this basis, such that if I come along with any arbitrary state phi, and I act on that state with the identity operator, I get the state back again. This phi could be either the 0 or 1 states, or it could be any linear combination of 0 and 1 states. Then we define the creation and annihilation operators. And these can be defined in terms of projectors in this way. For example, this thing that we called C dagger turns the 0 into the 1. What do I mean by it turns the 0 into the 1? What I mean is if I act on the 0 state with the C dagger, I get the 1 state. If I act on the 1 state with the C, I get the 0 state. And this just follows from these orthonormality conditions. However, notice that if I act on the 0 state with the C operator, I get 0. This is encapsulating the idea or the notion that I can't empty further an already empty state. If there are 0 particles in the state and I try to annihilate that state, there's nothing there to annihilate. What about this second equation? This tells us that if I try to create an electron in a state that's already occupied, I get 0. And that actually embodies the Pauli principle, which tells us that for fermions, the maximum number of fermionic particles in a given quantum orbital is 1. So I can't create another electron there. That, of course, would be different if we were talking about bosonic species. We also introduced the idea of a number operator, n hat, which is defined as C dagger C, such that if I come along and act on a particular state, ket n, with this number operator, I get the state back again multiplied by n. And n here is just 0 or 1. It's a quantum number, if you like, labeling our basis states. N is 0 is the empty state, n equals 1 is the occupied state. So we see from this equation that these basis states, these qubit states, are actually eigenstates of this number operator. In fact, that's why we call it the occupation number formalism. That's a slightly more telling phrase than calling it second quantization. And in fact, that's why we labeled these states by 0 and 1 in the first place, precisely because they are eigenstates of this thing called n hat, which is the number operator. Finally, we derived, using what's here, the anti-commutation relations, meaning that if I take C dagger C and add to it the combination C dagger, that's equal to the identity operator. Whereas if I take the anti-commutator of C and C, or C dagger and C dagger, I get 0. Okay, so that's everything that we looked at in the last lecture as a summary. And this is just for a single quantum particle. However, it's very important that we establish these foundational algebras very carefully so that we can build it up. It's going to require a bit more efforts to do 2 particles, but we'll see that once we have 2 particles, we actually have everything we need from a formalistic point of view to describe states involving 10 to the 23 particles, which is what we have in condensed matter systems. Actually solving those models is a different matter, and we'll come on to that in due course. This lecture is just about the formalism. Okay. So let's now look at the situation for 2 quantum particles. So first of all, let's look at orbital number 1. In orbital number 1, we have a Hilbert space that's 2-dimensional, and we can either have a 0 or a 1 state. However, I want to label that this is the states of our orbital number 1, our quantum state number 1. So I'm going to put a subscript 1 outside of this ket here, which tells us that we're talking about orbital number 1. Likewise, for orbital number 2, I have 2 possible states, 0 or 1, but for this two-dimensional Hilbert space associated with orbital 2, for each of these orbitals, I have associated creation and annihilation operators, which behave in the way that we might expect for a single particle. So I can write things like Ci dagger acting on a state, an empty state in orbital I, gives me the one state in orbital I. Likewise, I can do Ci acting on the one state in orbital I, gives me the zero state in orbital I. Whereas, if I act with Ci on the empty state in orbital I get 0. And Ci dagger acting on the one state in orbital I also gives me 0 due to the Pauli principle that we just discussed. The commutation relations of these Ci and Ci dagger operators are just those that we've been discussing, namely that Ci with Ci dagger is equal to 1, whereas Ci with Ci and Ci dagger with Ci, these anti-commutators are equal to 0. And all of this that I've written down here defines completely the operator algebra for each of the two sides. In this case, we've got orbital 1 and 2, so I is either 1 or 2. However, it does not yet tell us everything about the combined system of two orbitals, because we don't yet know how the operators act on, for example, how C1 acts on orbital 2. We don't yet know, for example, what the commutation relations are, the anti-commutator, for example, of C1 with C2 dagger. Those kind of things we've not yet worked out. Before we get on to that, let's look at the states of our combined system. So far, we've just looked at the two-dimensional Hilbert space for orbital 1 and the two-dimensional Hilbert space of orbital 2. Now we need to think about the combined system of two orbitals. And what we're going to see is that we have a vector space that spans both orbital 1 and orbital 2, and we construct these by using the direct product of the two individual vector spaces. So the combined system has states that I'll label psi. Let's say psi 1. 1 here is just an index which distinguishes the different psis. Psi 1 will, for example, be the empty state in orbital 1 combined with the empty state in orbital 2. And this cross in the circle here is, of course, the direct product, or the tensor product. That's not what I wanted to do. Okay, what other kind of states of the system can we get? Well, we can just enumerate them all. So, for example, let's imagine a state psi 2, which is an empty state of orbital 1, but a full state in orbital 2. And likewise, we can just fully enumerate all of the possibilities. And there are only 4 possibilities, because we have 2 fermionic particles that can either be empty or full. So why do we have 4? Because for each of the 2 possibilities for orbital 1, I have 2 possibilities for orbital 2. If I were to have 3 sites in the system, then for each of these 4 states that I've written down here, I would have a possibility of either 0 or 1 in site number 3. So then I would have 8 possible states. So the total number of states of a system of n particles, n fermionic particles, is 2 to the n. And you see, this is the curse of dimensionality that you get in quantum many-body systems, because the size of the combined Hilbert space grows exponentially in the number of orbitals. Okay, but before we get there, let's just look at this simple two-body problem in which we have two sites which can either be empty or full, and therefore in total we only have a four-dimensional space. So let me just make a note on that. Here we have four possibilities. There's a four-dimensional state space. So let's look in a bit more detail about what this space is that these states live in. So the basic arena wherein n-body quantum mechanics takes place is the product space of single particle Hilbert spaces. Okay, so what do I mean by that? Well, first, let's organize our states according to the number of particles that they have. First of all, let's write down the total number of particles. And I'll call that capital N. And that's just the sum of the number of particles in each of the individual orbitals. In this case, I is just equal to 1 or 2, because we just have two sites. But already here I'm allowing it to be a little more general. So if we have a look at the n equals 0 situation, that's just the state that I called psi1, which is nothing in orbital 1 and nothing in orbital 2. If I have a look in the single particle sector, then I actually have two states, psi2 and psi3, as I called them, where I have one particle in the system, and it's either in orbital 1 or orbital 2. And then if we look in the two-particle sector, again, there's just a unique state which I called psi4. And this is where I have one electron in both orbitals. And there's only one way of doing that. So I have this degeneracy, if you like, of two different possibilities of arranging one electron in a two-orbital system. So n-body quantum mechanics occurs in the product space of single particle Hilbert spaces. So let's denote the single particle Hilbert space, which means single particle means total n equals 1. Let's denote that as this curly h object, and that denotes a Hilbert space. And you can see that in this case, with one electron in two orbitals, there are two possibilities. But let's say I had three orbitals and one particle, then there'd be three ways of putting the particle amongst those orbitals. So if I have n-body system, this lives in a Hilbert space which is the product space of the single particle spaces. So h to the n means we have n copies of our single particle Hilbert space. And this can be denoted using this direct product symbol. So for n-body system, I have the direct product of n single particle Hilbert spaces. Now, an n-particle state will, in general, consist of a linear superposition of basis states living in the n-particle Hilbert space. So what about the larger space that contains any number of particles? N equals 0 particles, n equals 1 particle, and so on. This larger vector space of a multi-orbital system with any number of particles, n, is called the Fock space, and we denote it F. And again, I use this curly F to indicate that it's a space of states. We define this as the direct sum of the n-particle Hilbert spaces. So each one of these Hn is a Hilbert space with a fixed particle number n. And then we take all such Hilbert spaces, including the one with 0 particles, and that constitutes the full Fock space. It is a space large enough to accommodate a state with an undetermined number of particles. Furthermore, let's have a closer look at the Hilbert space with 0 particles. This is a one-dimensional Hilbert space, which describes the sector of the theory with no particles, and it's a single normalized state, and we call it the vacuum state. And we denote this vacuum state as, let's say, either 0, indicating that there are no particles present, bearing in mind that this is a sort of shorthand notation for a full state spanning all orbitals, or maybe more conventionally, we just write a ket with the word vacuum in it, indicating that there are no particles in here. If we have 2 degrees of freedom, 2 quantum orbitals, that is, then the states that span the full Fock space are precisely these n equals 0, n equals 1, and n equals 2 states that we saw before. So we would have that this Fock space is spanned by n equals 0, n equals 1, n equals 2 Hilbert spaces, which is precisely these set of states psi1, psi2, psi3, and psi4 that I enumerated on the previous slide. So a given wave function of some system, whatever it might be, may comprise a superposition of states with a definite n if n, the particle number, is conserved by that Hamiltonian. However, there are also models that do not conserve particle number, at least not in an effective sense, for example, in the theory of superconductivity. And those kind of states, by definition, need to live in this wider Fock space rather than in a Hilbert space with a definite n. Now, the identity operator must be something that spans the full Fock space. So in the 2-particle system, we would define our unity operator, our identity operator, if you like, as something that spans all possible states of any particle number. And again, the defining property of the identity operator is that we can apply it to any arbitrary state living in the full Fock space and get that state back again. Okay, what does this actually look like for the case of our two orbital system? Well, we can just write it out in terms of the occupancy of the individual orbitals. Which takes a bit of time to write out, but let's just do it once. And then we'll have it. Okay, so we have basically all possible combinations for the occupancy of the 1 and 2 orbitals, and then we have projectors onto those states, and they span the entire Fock space. Okay, so what about the many-particle operator algebra for two particles? So we defined earlier this state psi1 to be exactly this state with no electrons in it. This is actually the vacuum state. It's the no particle state. That's fine. What about psi2? Psi2 we defined as being no electrons in the first orbital, but one electron in the second orbital. The point of using our creation and annihilation operators is that having defined a vacuum state, we can generate all other states from that. How? Well, to generate this psi2 state from the vacuum, we simply operate with the C2 dagger on the vacuum. That creates a particle in orbital number 2. Good. Likewise, for our psi3, we defined this as a single particle acting, a single particle occupying orbital 1 and no particles occupying orbital 2. And this can be obtained from the vacuum state by simply creating a particle in orbital number 1. Good. What about psi4? This is where we have a single particle in both orbitals. Now here we have to be more careful. How do we generate such a state from the vacuum? Well, we need to create an electron in both of the orbitals, but we have to worry about the order in which we do this. We know that quantum mechanics in general has non-commuting operators, and so the order of operation matters. In particular, due to wave function antisymmetry, the order of the operation matters. So how do we proceed? Well, let's just define this psi4 state to be obtained from the vacuum by acting with C1 dagger and C2 dagger on the vacuum in this way. So what does that mean? Well, let's have a look at this combination here, C2 dagger acting on the vacuum. Well, we see from this expression that C2 dagger acting on the vacuum is precisely the definition of our psi2. So this object is psi2. So psi4 is actually, according to this definition, generated from C1 dagger acting on psi 2. What that, of course, means is C1 dagger acting on something with no electrons in the 1 orbital and 1 electron in the 2 orbital. And therefore, we know, according to the definition, that psi 4 is just C1 dagger acting on psi 2. And that gives us this state, which is 1 electron in the 1 orbital and 1 electron in the 2 orbital. Okay, good. But now we have an interesting question, which is what happens if I apply the operators in a different order? What about if I do C2 dagger, C1 dagger acting on the vacuum? What does this give us? Well, we apply the same logic. First of all, we act starting with the rightmost operator acting on the vacuum, which is C1 dagger acting on the vacuum. And then we see from our definitions that C1 dagger acting on the vacuum is our definition of psi 3. Oops. So C2 dagger, C1 dagger acting on the vacuum is equivalent to saying it's C2 dagger acting on the state psi 3. So this is not quite the same, as you can see, from our previous calculation, where we had that C4 dagger was equal to C1 dagger acting on psi 2. So are these the same things or not? Well, to answer this question, we should look at the wave function asymmetry with respect to exchange of particle labels. We're dealing with fermionic systems, so we should get a minus sign when we interchange particle labels. So if I exchange the labels 1 and 2, I should get a minus sign. So how does that look? Let's do it in a sort of operational way. Imagine that I have an operator, P12, which is like a permutation operator. Which swaps 1 and 2 labels. Okay, so we have some such permutation operator. We know, because of the wave function antisymmetry, that if I apply this operator to a given fermionic wave function, it should give me minus the state back again. Okay, this is the concept of the fermionic antisymmetry of the wave function. So how can we use this information? Well, let's just act with this permutation operator on our state psi 4. But let's write out psi 4 according to our definition of C1 and C2 acting on the vacuum. And the permutation operator swaps the 1 and 2 labels. So this gives me this state, or this set of operators acting on the vacuum. But we know this is equal to minus psi 4. And minus psi 4 is minus the state that we started with. So, rearranging this equation, we get the following operator equation. We get C1 dagger, C2 dagger, plus C2 dagger, C1 dagger, acting on the vacuum gives us 0. So as an operator equation, we see that the anti-commutator of C1 dagger and C2 dagger is equal to 0. And so here we've actually managed to derive, basically from first principles of the fermionic wave function antisymmetry, a commutation relation between operators on different sites. So that's an important relation. And similarly, by the same kind of argumentation, it's easy to show that C1 with C2, the anti-commutator of those things, is equal to 0. And a little more involved to show, but you can also see that the anti-commutator of C1 with C2 dagger is also equal to 0. And so, overall, we've derived the canonical fermionic anti-commutation relations which define the operator algebra of many particle quantum systems. And obviously this is a big deal. So let me summarize them here. And let me just summarize those. We have that the anti-commutator of Ci with Cj dagger is equal to delta ij, the Kronecker delta, which, just to remind you, means either 0 or 1. It's 0 if I is not j, and it's 1 only if I is equal to j. And then we have that the anti-commutator of Ci with Cj, or the anti-commutator of Ci dagger with Cj dagger are equal to 0. And together these define the fermionic operator algebra. And of course the punchline is that the order of operation of these creation and annihilation operators matters. The order of operation is encoded in these anti-commutation relations, whether or not you get a plus or minus sign, and that in turn enforces the fermionic wave function antisymmetry. So by using these anti-commutation relations, we can now forget about the fermionic wave function antisymmetry. It's already built into the operator algebra, and that's the huge advantage of second quantization. And we can define a generalized state as being something that is the result of an ordered operation of operators on the vacuum. So for example, imagine I have a state specified by occupation numbers n1, n2, n3, n4, and so on, up to n for n orbital system. What I mean by this is that there is n1 particles in orbital 1, n2 particles in orbital 2, n3 particles in orbital 3, and so on, all the way up to capital N particles in orbital big N. And this is some generalized state where the ni's are occupation numbers, and they're equal to 0 or 1 only for fermions. And this state can be written in a sort of compact notation as the direct product of these single orbital states, and they, in turn, can be thought of as the product of acting on, this is the ordered product, of acting with a creation operator in site I, and I take this to the power of the occupation number, acting on the vacuum. So why is that? Let's say I have n1 is equal to 1 electron in orbital 1. Then I would have C1 dagger to the power of 1, which gives me C1 dagger acting on the vacuum. It creates an electron in the vacuum. Let's say in the orbital number 2, I have no electrons. That would be N2 is equal to 0. So I'd have C2 dagger to the power of 0, which is just 1. No operator there. But it's important to remember that this is an ordered product. So this is C1 dagger to the power of N1, C2 dagger to the power of N2, C3 dagger to the power of N3, and so on, all acting in the end on the vacuum. So a many particle state is generated in that way, and the total particle number in such a state is simply the sum over I of these individual ni's. So let's now look a bit more closely at the number operators for many particle systems and the occupation numbers. We've already been sort of implicitly using these occupation numbers, so now let's examine that in a bit more detail. Let's consider the commutator of a number operator ni with, for example, the creation operator Cj dagger, and remember that the number operator ni is defined as being Ci dagger Ci. Okay, so let's just write it out. This is Ci dagger Ci, Cj dagger, minus, because we're talking about the commutator, Cj dagger Ci dagger Ci. So let's try to simplify this a little bit using the anti-commutation relations that we know. In particular, recall that Ci dagger Cj dagger, the anti-commutator of that, is equal to 0, which tells us that Cj dagger Ci dagger is equal to minus Ci dagger Cj dagger. So we can actually use this relation in here to swap the order of Cj dagger and Ci. And that gives us, let's just write out the first term again, Ci dagger Ci, Cj dagger. And then I'm going to swap the order of those two terms and give me Ci dagger Cj dagger Ci. But to be able to compare the two terms in this sum, we're not quite done yet, because we still have this Ci dagger here. And so for this pair of terms, we'd like to be able to swap those, the order of those as well. And we can do that using the anti-commutator of Ci with Cj dagger. And this is equal to delta ij. It depends on whether we're talking about the same orbital or not. Okay, so using this expression, we can write that Ci Cj dagger plus Cj dagger Ci is equal to delta ij. We can substitute that in here. And then we'll end up with, again, let's write the first term, Ci dagger Ci Cj dagger plus Ci dagger. And then we're going to swap the order of Cj dagger and Ci to give us delta ij minus Ci Cj dagger. And so when we tidy this up, overall, we find that this is equal to Ci dagger delta ij. The other terms cancel. And in particular, if I is not equal to j, then we've discovered that ni and cj dagger, the commutator of these things, is equal to 0. So they commute. This has an important implication because we can see that a generalized state written in this occupation number basis is an eigenstate of the number operators. What I mean specifically is the following. Imagine that I act with a number operator nj for orbital j on a particular state n1, n2, n3, and so on up to n, capital N. This is equal to nj times the state back again. And here, notice importantly that this thing is the number operator. This is an operator, note the hat, whereas this is actually the quantum number. This is an occupation number. It's just a number, not an operator. So you see that nj is an operator, nj hat is an operator, nj is the eigenvalue. This is an eigenvalue equation, and we see that these states are eigenstates of the number operators. So how did I get that? Well, let's use our definition of a generalized state and the anti-commutation or the commutation relations. So nj is going to be acting on the state and using our definition of this ordered product of operators acting on the vacuum. Again, let me just write that out in this alternative notation, or slightly clearer notation perhaps for the purposes that we're going to talk about now. This is C1 dagger to the power of n1, C2 dagger to the power of n2, and so on, all the way up to, let's say, Cj dagger, whatever j is, and that's to the power of nj, and so on, all the way up to Cn dagger to the power of n, capital N. And all of that, that string of creation operators is then acting on the vacuum. Now, what I want to do is act with my number operator nj on this state and see what I get. First of all, what I'm going to do is swap the order of these two operators, which is equivalent to saying I'm going to sort of hop, if you like, the nj operator through this C1 dagger operator. And we can do that using the commutation relation, because j in this case is not equal to 1. J is somewhere else in the string of operators. We see it over here. So j is not equal to 1, and we know that n j, the commutator of nj with C1 dagger, is equal to 0 for j not equal to 1. So in practice, what this means is that NJC1 dagger is equal to C1 dagger NJ. We can swap the order of these things. So I can just swap the order, and I would get that this thing is equal to C1 dagger N1, and then NJ, and then C2 dagger N2, and so on, all the way up to CJ dagger NJ, and then I have some more operators all the way up to Cn, acting on the vacuum. Good, and you can see that that same logic applies. I can move this operator, using this commutation relation, I can move this operator through this string of creation operators all the way, however many times it requires it, all the way up until I finally get to CJ dagger, and there is a bit of a difference. And it's different because now we're acting with a number operator on the same orbital as we have a creation operator for. So to be able to swap the order here, I need to consider a commutator that looks a bit like this. NJ with CJ dagger, but there's a bit of a difference because this is CJ dagger to the power of NJ. This looks like a slightly funny object. So what is this going to be? Well, let's consider the case when NJ is equal to 0. If NJ is equal to 0, then we have CJ dagger to the power of 0, which is 1. And obviously the number operator commutes with 1. It's not an operator, it's just the number 1. So the commutator NJ with 1 is equal to 0. On the other hand, if NJ is equal to 1, then I have CJ dagger to the power of 1, which is CJ dagger. And then I have to consider the commutator NJ with CJ dagger. And we just work that out. That gives us CJ dagger. So you can actually combine both of these together and obtain the following: NJ times CJ dagger to the power of NJ. If NJ is equal to 0, you get 0. If NJ is equal to 1, you get CJ dagger. Okay, so we can actually substitute that into our expression and use it to obtain the following result. I can express my generalized state all the way up to the term j, and then I'm going to have nj into cj dagger nj plus cj dagger to the power of nj times nj hat, that is, of course, and so on all the way up to our nth orbital, and all of this is acting on the vacuum state. Okay, so we have the sum of two terms after all of this complication. One of the terms has the nj to the left of the cj dagger operator, and one of them has nj hat to the right of the cj operator. The latter term, the one with the nj operator acting to the right-hand side of the cj, we can just run that all the way through and act on the vacuum without any other complications. We've already commuted it through the cj operator. So that's just going to be nj acting on the vacuum, which is going to equal 0. Then we have this second term here. This is just a number. This number can be brought out to the front here. And then I'm just going to have nj acting on this string of operators. And that's just the original state that we started out with, which gives us nj, the occupation number of orbital j, multiplied by c1 dagger to the power of n1, c2 dagger power of n2, and so on. And all of that acting on the vacuum. And of course, this then gives us our original state back again. Okay, so indeed we've proved, after a bit of algebra, that these occupation number basis states that I've written down here are eigenstates of the nj operator with eigenvalue nj. And that's, of course, the whole reason why we're doing this. Just wanted to show you this once rigorously. We don't have to do this every time, certainly not. The whole point here, though, is to derive it once, and then once we've derived it, we don't have to worry about it ever again. So indeed, these basis states that I've written down here, with these occupation numbers n1, n2, n3, and so on, they're actually eigenstates of nj hat with eigenvalue nj. One other important thing that we need to prove is that the commutator of ni with nj is equal to 0. And that's extremely easy to show. Again, we can use the commutation relations and the anti-commutation relations of the operator to show this. And what this tells us is that we can form a simultaneous eigenbasis of the number operators we can label our states not just according to the eigenvalue of nj hat, but also of ni hat or nk hat or whatever. In fact, we can label our states according to the eigenvalues of all of the occupation numbers, and indeed that's the whole point. So what we prove from this is that a basis state labeled by the occupation numbers are eigenstates of the occupation operators, the number operators. Simultaneous eigenstates of all of those number operators, and n1, n2, n3, and so on are quantum numbers. So they're good quantum numbers to actually label these states. And this is what we finally call the occupation number basis. Okay, so I don't need to do this ever again. I've basically proved that in fermionic systems, I can write down a good basis of my states according to the occupation numbers. And I just derived this from first principles, just using basically the idea of the wave function antisymmetry and the Pauli principle. And what I arrived at is this nice, efficient way of labeling the states in this Dirac notation according to the occupation numbers of the different orbitals. So, for example, with two orbitals that we were looking at explicitly earlier, I could have a state defined n1, n2. This means n1 in side 1, direct product with n2 electrons in site 2. I can act on this thing with n1 hat, and I will just get the number of electrons in n1 back again. But I can also act on this state with n2, and I just get n2 times the state back again. So we've rigorously proved that this is a good way of labeling the states, and it's therefore a good basis for future calculations. And we'll really see the power of this shortly. And notice, of course, that all of the quantum mechanical properties that we want are encoded through the operator algebra already. We don't have to worry about them again. One final thing I want to say is that the total number of electrons can be obtained from this capital N hat operator, which is just the sum over all of the individual Ni hats, and the total number of electrons, N without the hat, is therefore just the sum over all of the individual occupations. And obviously, therefore, because of the linearity, if I act with capital N hat on a given state, I just get N times the state back again. It is indeed an eigenstate of the total number of electrons as well as the individual occupation numbers. Okay, so that's basically everything that I wanted to say about the occupation number formalism, second quantization formalism. What we now want to do, of course, is to put all of this into action, and we'll see that it's really a very straightforward and elegant and powerful way of doing quantum mechanics. All of this very technical stuff that I did so far was to set up the formalism itself. Applying the formalism, we'll see, is straightforward.